All right. Here's what we're going to be looking for. I think they can read that. Okay?
Yeah, I was just thinking.
Rob, is that enough so you can read? Is that big enough print?
That's fine. Looks good.
All right, great. All right, what we're looking for in strength of materials questions on this quiz, we're looking for the basic stresses that are induced in these members when you load them. And then a second requirement, we're looking for the resulting deflections that are caused in the structure. We come up with derived equations, which are not perfect, but they give a very close idea of what stress level you can find and what deflections will be induced in these structures. And then it'll be your job to make sure these don't exceed some allowed value. We're basically looking at the type of stresses in the members, the easiest ones, simplest ones, the direct stresses, like a stress in a bolt, a stress in a tension member. Those stresses come in two flavors. They come in normal stresses and shear stresses. The normal stresses are the ones that act along the axis of the member, and the shear stresses act across the axis of the member. Then a second class of stress is when you twist a shaft. For example, a shaft, a drive shaft in a tank or car. The twisting of that shaft causes torsional stresses, and those are actually also shear stresses. Those shear stresses are the same kind of stresses that you get back up here in direct shear, what they call. Then your bending stresses. The bending stresses are actually tension and compression. So we've really still only got two brands here. We've got normal stresses. The normal stresses include tension. Got to spell it better than that. Tension and compression. And then the shear stresses are wiping stress. It's like the stress that goes between your shoes and the floor when you decide to leave the room. Then pressure vessels basically have nothing in them but tension. Then on combined stresses is any combination of that set of stresses, tension and compression and shear from various and sundry loading conditions. And finally, columns, they have compressive stresses in them, but their failure mode is actually one where the column buckles. And that phenomena is like when you take a meter stick and you press on the meter stick, and all of a sudden, with very little or no warning, the stresses exceed some level that cause the thing to pop out to the side about its weak axis. All right, then on the deflection side of things, you have basically axial deformations, twisting or torsional deformations, and beam deflections. I guess you could also add column deflections. We don't usually calculate those because once it's popped out to the side, everybody's laying on the ground anyway, so that's of very little use to us. We'll usually calculate the load at which the first little tendency to buckle to the side occurs, and then we quit. We back off from that value. All right. Back to the beginning, direct stresses. Direct stresses are our tensile stresses and our compressive stresses and our shear stresses.
Dr. Lowery?
Yes, sir.
If I can interrupt with the deflection, You mentioned actual deformation and column. Is there similarity between the two? What would be the example of the difference?
In a column, if you were to take this structure, which is relatively short and squatty, and put a load on it, a load P, if it's relatively short and fat, then I can calculate how much that member will squat down. We would probably call it delta. All structures deform like that under load. You may not be able to see them, but when you sat in the chair, it got a little bit shorter. Now, in a column, that also happens, but again, it's a very small number. This kind of deflection in columns is what I'm talking about. That kind of deflection is failure, when it has dumped the load off on the floor. So although this number can be calculated for various loads, it's usually of not much interest to you in the design phase, because your interest is to make sure that this critical buckling load is stayed well away from.
Okay, thank you.
Okay.
Got it.
All right. Direct stresses. Your basic equation for tension and compression stresses is that the stress is equal to load over area. P is your load. Probably is normally going to come from the problem itself. The problem will state that it is 400 pounds per square foot of loading on a flat slab carried by a beam over to a support reaction, and you calculate how much load there is on it. That's the load. And divided by the cross-sectional area of the shape that you're holding the load up with. We use the symbol sigma for stresses. We could use the letter S, but then the architects would understand what we're doing, and they would get in the act. Same way with the letter tau. It's nothing but a shearing stress. Same thing, load and area. The shearing stresses are actually wiping across the face. I'll show you some of those in a minute. You have some in the notes. And the tensile and compressive stresses act in the direction of the axis of the member. All right. And I'll tell you, I forgot to number my pages when I sent you with yours already numbered, and I'm hoping I got the same numbering. Does that look like what you got on page 6, Rob?
Same page, yep.
All right, I'm in good shape then. Here's a bar. Someone has placed a load P, perhaps 600 newtons. They tell me a newton is an apple. So that's about how much 600 newtons is, about 600 apples. Or perhaps 600 kips. Kip is nothing but 1,000 pounds. It's a nice convenient way not to have to write down 600,000 pounds of force. It is applied to a tension member. Someone has depicted the cross-sectional area by showing you what it looks like rotated 90 degrees from the true axis. They have cut a section out of the member and exposed the stresses inside of the member. He shows you that all these little stresses add up to the load P. The magnitude of stress he has shown there is sigma, and that's the stress. Stresses loads don't actually break things. It's really stress that breaks things. You give me a large enough member and I can hold up just about any load that you're willing to buy, that much steel to hold it up. But if the stress level reaches a certain level, then the structural member fails, and most all design is based on that fact. To make sure we know what tension is and compression, when the bar is stretched, when it has a tendency to get longer, we're talking tension, and when it is squashed, we say it's in compression. The load P on the left end has to equal to the load P on the right end, or the bar takes off down the road and we get to go down the road for free. So you'll always have these loads on the end of the two members are going to be equal. Now, a lot of times the problems on page 7 would be typical, and I guess I can zoom on some of them. A lot of times the loads on the structures will be kind of hidden. The loads are inside the structure, and you're asked to design the structure, or you're asked to tell me what stress is inside the structure. The way you get at those answers is you cut a thing called a free body out of the structure. In this particular case, I would show you there's a bar which has been opened up so that you can see the stresses inside of the bar. Those stresses are uniformly distributed. They're the same on the right as they are on the left, as they are in the middle, as they are on the front. They are of a magnitude sigma is equal to the load divided by the area. For example, if this particular bar has a 10 kip load, same as 10,000 pounds, and if it has an area equal to 2 square inches of steel, then I would tell you I can calculate the stress in the bar. Stress is equal to load over area is equal to 10 kips divided by 2 square inches of steel, and we're talking 5 KSI, or 5 kips per square inch of steel. That 5 KSI is the actual stress in the member. It would be compared against some allowable, probably given in a code, so that you can see if past experience shows that stress is acceptable or if it's not acceptable. All of these equations can be wrapped around in a different direction if you like. The basic equation could be used to tell you how much load is acceptable on the member, simply by putting P on the other side. You'd say that P allowed is equal to the stress that is allowed multiplied times the area that you intend to supply, or how much steel you're willing to purchase for me. And the last way, you could tell me how much area is required by simply solving for A is equal to P over sigma. That would be P, how am I going to say that? P put on the structure. Give me a short word for P put on the structure. P carried.
PX. Well,
tell me again, Rob.
Maximum.
Okay, hey, I love that. Maximum load you intend to put on the structure divided by the stress that is allowed. They work nicely. So if the design equation says you got this much load, and use the ACI specs or something, you go in the specs, you find out how much stress they'll let you put on it, and how big does it have to be. The basic equation tells you how big it has to be. If he gives you the size and how much stress is permitted, then you should be able to tell him how much load is permitted on the structure. And then finally, if you know the load and you know the size, then you should be able to compute the stress that's actually in the structure and compare that with an allowable. Now then, let's say that in this case we've decided to include the weight of the structure This is a 20-foot long piece of bar, so that's a reasonably heavy piece of bar, and it may change the answer for the stress in the bar slightly. So I'm going to calculate that the weight of the bar. Now this, of course, depends on how much of the bar I cut off. If I cut off 10 feet, I get one answer. If I cut off 18 feet, I get another answer. But the worst stress in bar BC would be when you get its full weight right up there at the top of the bar. So if I want to know the worst stress in bar BC, I'd probably go ahead and cut off the whole 20-foot chunk. Then the weight of the bar is equal to, it's going to be 20 feet times 12 inches in a foot. Now that's the length. I multiply that times 2 square inches of steel. And we just decided it was steel, I notice. If it was Jell-O, we'd use a different weight. So now we have the volume of steel. The cross-sectional area times this length gives me the volume. And then I multiply it times how much steel weighs, 0.283 pounds per cubic foot.
Cubic inch.
Thank you, Kelly. I knew I was paying you for something here. Per cubic inch. And is that already calculated? 136 pounds. Thank you. So on top of the 10,000 pound force, which didn't cause a lot of stress already, steel's probably good for 20, 30 KSI, we're adding a mere 136 pounds, and that's why many people neglect the weight of the structure. But if you want to be real picky about it, I would now tell you that the stress up at the top of that bar is equal to 10,136 pounds divided by the cross-sectional area of 2 square inches, and that slightly increases the stress in the bar. 5.068. Not enough to matter, not within engineering accuracy. If we were going to the moon and that was how many degrees we were off, it would probably matter. But it's most unlikely the guy will come up with 10,000 pounds of sand with that kind of accuracy, so probably it doesn't make much difference. Now the next bar, the top bar, is getting kind of fat, not to mention it's almost twice as long. When we find out how much stress is in that bar, we will have to include not only the weight of the bottom piece, but the weight of the top piece too. And we'd calculate everything the same way. We would calculate the volume and multiply it times how much steel weighs a cubic inch. And if you check that out, you'll find the equation comes out, stress is equal to 10,849 pounds, including the weight of both bars. So now we have increased the weight about 1%. Still pretty small. Probably we'll never get that bar to a 2 square inch size. Oh, I guess also what size I use. 6 square inches for this top bar. 6 square inches of steel. The only way to get that bar to 6 square inches with 2 decimals or 3 decimals of accuracy like that would be to grind it off with sandpaper, and that's not likely to happen. Divided by the 6 square inches of steel that I assumed the bar to be, and it comes out with a stress of 1808 PSI, or KSI. No, that's PSI. Knock it down by 1,000 to get it into KSI. Now you'll notice you have 2 different stresses. Sometimes it's kind of hard to see which stress will control, and you have to calculate both of them. In this case, on a quiz, you probably would come out ahead by not bothering to calculate the stress in the top one. It's got to be much less than the stress in the bottom one. The bottom bar is so much smaller, it's a factor of 3 times smaller. The 10,000-pound load is about the only loads that's there, so the stress in the bottom bar is obviously going to be bigger. If you see some ways, some things you don't have to check, probably saves you time not to check them. All right. Another example on page 8. In order to solve for the forces inside of these bars, I would cut a free body by cutting a free body, I expose the stresses inside of the bar. And since I can see the stresses and the forces inside of the bar, I can solve for what the bar was purchased for. Why did I buy that bar? Well, I bought that bar to hold some load. How much load? Draw a free body of the bar. Show the 8-kip load involved. Show an unknown force inside of the bar, because I don't know what the answer is inside the bar. Use equations of statics. Some forces horizontal is equal to 0. And so, not much doubt, 8 kips of tension inside of the bar. Same way on the next piece of the bar. Draw me a free body. Put all the forces involved on the free body. Put the unknown force on the free body. Many times, although you might look at that force and say, whoops, that wasn't real smart, but many times you really can't outguess which way that force is going to go. The problem just gets too nasty for you to tell. It's just about as easy to always put the force in tension. If your equation of statics says the answer is a minus, that simply means that the arrowhead was guessed in the wrong direction when you began. That's what will happen to us here. We'll say sum forces horizontal equals 0 equals minus P minus 10 kips plus 8, and solve for P by moving it to the other side of the equation. It says P is equal to minus 10 plus 8, minus 2 kips. Now, the minus sign really does not mean that P goes left or that P goes right. In this equation, when you said minus P, the minus P really meant something. It meant it goes to the left. The minus 10 meant it really goes to the left. The plus 8 means it really goes to the right. But when you start picking things up and moving them on either side of the equation just so you can get an answer, those signs no longer mean the same thing. The minus sign now simply means, I don't know which way it used to be, but it was wrong. That tells you that whatever way you guess the arrowhead P is pointing the wrong way. So in our case, we would say that P load is 2 kips of compression. Many times, like in this case, someone's in a hurry and they'll find that the load P is equal to a minus 2 kips, and it does look like it's pointing in the minus direction. They say, well, okay, I guess that's right. That's not what that means. The minus sign means it is not a tensile force, it is actually a compressive force. And then you do the same thing for the last free body. Obviously, you probably don't do this but once or twice and you start getting the idea. So you don't draw a whole free body. You simply look at it and say, all right, 8, 9, 10, 11, 12, there's 13 kips pushing to the right on something. Somebody's trying to help by pulling 10 kips to the left on that thing. It is out of balance 3 kips to the right, and therefore I need another 3 kips of force to the left, pulling on the free body. So the force in section A, we don't really have a name on these things, but the force in that big bar is equal to 3 kips of pulling, 3 kips of tension. Alright, now then, the stresses in each of those sections would be nothing to it, now that I've got the forces. For instance, the stress in this section is the stress that's distributed across this area, and the stress is equal to 8 kips divided by, that area is shown as A3, it has no value. As soon as I found what the value was, I'd stick it in there, that'd be the stress. Same way on all the rest of them. You'd simply take the force applied across the cross-section, divided by the area of that cross-section, and that's the stress in there. Alright, now those are normal stresses. Those are tensile and compressive stresses. Other money-making type of stress is a shear stress, a wiping stress, a sliding stress. A piece of chalk, for instance, is very, very carefully designed to have low shearing stresses. They want little pieces to slide off when you wipe it across the board. They also try very hard to give it a reasonably high tensile and compressive stress so that when you bend it in pressing it on the board, it doesn't break in half. Here is a case where there is a force of 60 kips applied to a clevis or a yoke, and the piece of steel pulling to the right goes both above and below another piece of steel which is being pulled over to the left. In order for that bolt to fail, you would have to actually suck this little plug of steel right out of the center of the bolt. And that's really how I recommend that you find the area in these equations. You look at it, you say, well, it hasn't failed, it's not going to fail, I'm not going to let it fail, that's how come I designed it so it won't fail. But unless you can see it failed, it's kind of hard to get the cross-sectional area necessary for use in the equation. So what you should do is you should assume that this left-hand piece of steel actually just pulled straight out and did fail. And when these little pieces fell on the floor, you see this piece of the bolt is nice and shiny, and you also see this area underneath here is nice and shiny. All the rest of the bolt is nice and rusty. Well, that nice new shiny surface that you see is the failure area. That's how you tell whether or not you should be using the cross-sectional area of a circle or the cross-sectional area of a cylinder or whatever. In this case, I'm going to assume that the bolt has a diameter of 1.5 inches. And were it to fail, were it to come apart, a little plug of metal would come out with it and fall on the ground, and it would have a top shiny surface area and a corresponding one on the bottom. That's called double shear. And the cross-sectional area that used to hold up the load is the area of a circle, pi times the diameter squared divided by 4, and then it is times 2 surfaces. Oh, I sure am glad you're here.
Go ahead and call for Matt.
They'll have to call from that. Do they know? I'm not sure Ramsey's there.
One of them is.
Does the audio drop at the same time as the video? Uh-huh. Ooh. And I just about said, you might as well go ahead and go, because I'm sure, you got other things to do. You ain't going anywhere. How do we know it's not our fault, that we need to call them?
Well, I can't, I've already tried to initiate a call from that
I
end,
see.
and it doesn't hook up.
I see. Did you see Ramsey in there? He's probably not.
His assistant's in there.
Is he? Okay. Oh, we got a nice break.
Hello? Is it Ramsey? Hey, Ramsey? Yeah. I was looking for Ramsey. This is Gary Betts at Texas A&M. Yeah, and our class, yeah. Is the person there that knows how to dial up? No, there should be...
Do you want a break? Now's a good time?
Well, Ramsey is supposed to, or Robin or somebody, was there a gal? You handed out your little sheet.
Did you want to go over this?
Oh, yes, I certainly do. Do I not
Is it
have that? No, I don't think I have that. And I do
Because
want
I've
to
already
show them
tried to
that.
initiate the call.
That might be a good
from
time to
this
get
end,
into right after this one, then,
So-
because...
That sounds good.
All right.
Really, I meant to get into it before this, simply because it was still tension.
Yeah.
Okay. And I also need to, that got left out of the notes.
Well, I don't know what kind of system he has to dial in, but you need to dial in my 2 phone numbers, okay?
Now, are they using an actual telephone lines to do this?
Well,
Whereas
there's special
No, that's
lines
not
that are
it.
Yeah.
dedicated.
It should be, say something
Okay.
about video call. Is there are you using a mouse, is there a mouse thing on a tablet? Anything around there? Or say, okay, is there a thing where you, yeah, is there a place where you can click on video call?
I got what's interesting.
Connect is,
I guess it's a lot more.
over there, I
system.
believe, to the
Like
right
the news
someplace, it should say,
stations, for their live.
Okay.
Satellite feeds.
Yeah,
yeah, that's it.
Much more expensive, probably 10.
Okay. Okay, did you connect? Hit connect?
Much better picture too, of course.
and audio and everything.
Does it say dialing or anything?
Unlike everything
Yeah,
else,
well,
everything's
just wait a
coming down
minute.
in price.
Interesting, last time we
Yeah.
didn't have this, but,
Well, that means it's trying to call, but, yeah, that's a good sign. You should get a message or something saying port A connected, and then port B connected.
So are they an outside firm?
no, this is us.
I mean, this is A&M?
Gary will explain it.
Oh, okay.
Nikki Harris is also in that office, and they kind of run these labs,
I see.
keep them going.
People at Hood, are they...
Do you still got that message up
they're
there?
independent?
No, the guy there is a guy
Okay,
named
by now
Ramsey.
you got
He's
my
in the
motor
military, and
tree.
they have all this equipment that they bought.
Hit hang up?
He kind of runs it.
Yeah. Okay, wait a second. And go up and click on that connect. Click twice instead of, yeah. Okay. Now we're making somewhere.
Good.
Short night, otherwise.
It was really kind of fun, though.
Mm-hmm.
I just wish that there was, wish.
Okay, one of my motors is starting. We're coming through. Heck, fire, you guys could be telecom specialists in no time.
Is that part of the test, Lee?
Well, that's because only one of my modems is hooked up. He'll come in a minute.
Let's get on this. Yeah, you click on this.
Well, don't hang up yet.
Don't hang up yet.
Look at that.
Okay, now we should come
Yeah, 3 of them snuck out.
You got it?
We can see you.
All right, good deal. Now we can hang up. Bye-bye.
Oh, Rob took a powder. Oh, there's Rob. Okay.
It was too early for a break, guys.
It was. All right. Kick back on. There we go. All right. We were talking about failures. We were talking about the area here. This area calculates, you crunch it in the calculator, 3.53 square inches of steel has to fail in order for these two pieces to separate. A lot of people say, well, what if just the top half fails? Well, then the bottom half is still hanging on, and if the bottom half doesn't let go along with the top half, then I have time to get out and failure has not occurred. Only if both surfaces come loose do we have a failure. Then the stress, we would use the symbol tau as opposed to the symbol sigma, as it's a wiping stress. Hey Rob, if you find out that's not the right answer, I don't want to hear about it. Tau is equal to 60 kips divided by 3.53 square inches. Rob's from Missouri. 16.98, what is our units? Kips per square inch of steel. All right. Now, the real point for going over some of the basics like this is the areas that are holding these things together. You've got to be able to calculate them and get the right areas. For instance, here is a very similar situation. It's where a load P has been applied to some kind of a piece of steel. Probably that piece of steel used to be inside of a solid piece of steel, like so. And the guy is trying to put a hole in this thing by pressing with a die. And so he presses across the top of the plate, and he tries to poke this little plug out on the floor. And the question is, what stresses are induced in this little plug of steel? Well, in that case, although you still have a pi d squared over 4 area showing, that's not the area that's holding the structure together. In that case, when he tries to push the plug out of the plate, this is the area involved, the area around the piece of steel, even though it is still a shearing stress working to resist that. So in that case, the cross-sectional area is equal to pi d, because that's the distance around the little plug, and then you multiply the length of that line times how long is the plug. The plug shows to be T, where the thickness will be 3/8 of an inch. So the general equation for the area involved is pi dt. It's like the surface area on a tin can, pi d being the distance around the tin can and T being how deep or how tall the can stands off the ground. So if our load P were 20 kips, just to pick a load, then we would say that the shearing stress is equal to load 20 kips divided by pi times the diameter of 1 inch times the thickness of the plate, 3/8 of an inch. And I'll never remember it if I don't tell you now. We do get some shadows on this from your hand. So those lights, even though they're kind of in the way, yeah, maybe next time we'll throw them back on there, because I think that kind of helps. Ooh, that's worse. Yeah, I was better with it. Okay, and then that comes out, ooh, that's interesting. Another 16.98 KSI, mere coincidence. All right. Now, this is not in your notes. I'll send it up with you. I'll send it up next time we send some stuff up, just as we'll call them supplemental notes. But a couple of the problems in the quiz, there we go. A couple of the problems involved plates with holes in them. And let me show you this one first. The equations are straightforward and simple. There's not much to them. Like I say, and we'll include them in a supplemental package. But if you have a plate that's got some holes drilled in it, as the load starts coming down the structure, it's going to hit the first weak spot and break across these holes. It's not going to break through 5 holes. It just wouldn't have much tendency to break across, and they'll come across here and then go through this hole and back over to that one. There's just too much steel involved. He's got no desire except to tear across the shortest, quickest, easiest way across the plate. So he tears across 2 holes. Now the gross area of the plate, with no deductions due to the hole, would be the width of the plate times the thickness of the plate. The net area takes into account the fact that there are holes there, and that simply is, again, the remaining width times the thickness. That means the thickness of the plate's still there, and this is the remaining size of the distance across the plate. You take how wide the plate used to be before somebody drilled holes in it, minus the number of holes in some holes, and the number of holes is, in this case, 2 holes. And then the amount of steel that each hole removed is the diameter of the bolt to be used, and then they add 1/16 of an inch for fit, to make sure the thing will fit together, because when you drill these holes, they're never in the perfect place, and if you don't use a little bit bigger drill than the bolt size you're going to use, you'll never get it together. Or they'll get it together, but you know, there won't be any threads left when they get through banging them through those holes with a sledge. And then, because you normally damage the steel to some extent around the hole, they make you add another 1/16 of an inch to the diameter of the bolt. So when you see a bolt, the guy says we're going to use a 1-inch bolt, the size of the hole is effectively 1 1/8 inch. Even if that's not the physical size, that's the structural size. Now then, there is a possibility that the plate might find it easier to fail back through that 3rd bolt, and you just have to check both failure patterns. In this case, they find that the net area is equal to how thick is the plate, and then you multiply it by how much steel is left. Well, how much steel is left is how wide it was before you drilled holes in it, minus, in this case, the failure pattern passed through 3 holes, so you put 3 holes here. Again, the amount of steel lost per hole is the diameter of a bolt plus 1/8 of an inch. And then, because this distance is longer going back into the plate, you get to add the sum of s squared over 4g. And the terms denote the spacing of the bolts, and that's along the axis of the plate, s, and the gauge size of the plate is the distance along the axis of the load, or it's like kind of like a train running down the plate. When a train runs down the plate, the distance between the tracks. They used to call it the gauge. That's probably where they got this name from. The gauge is the distance between the bolts in this direction. So in this case, you'd have two of these guys. You have two of these S squared over 4G terms because we have two slanted lines. Surprisingly, if you check the hypotenuse of a triangle, you don't get S squared over 4G. But the reason is because that slanted surface is subjected to a combined shear and tensile stress. It's not pure tension anymore, and so you get a little different area than you would think, strictly from the hypotenuse of a triangle. Okay. Now then, back to some shear on page 10. What do you think, Rob? I see 1, 2, 3 surfaces. You buy that?
Yep, I buy that.
Oh, Rob will buy anything. Hey, I got a bridge I want to talk to you about.
No, I see one surface in the middle.
I think that's right. You got one surface in the middle it takes to fail, because when this top plate takes off and goes to the left, and that bottom plate takes off and goes to the right, it's going to cut the bolt in single shear. So you're going to have 1 pi d squared over 4 quantity involved. Now then, a weld works pretty much the same way. The shortest distance this weld could fail is right across what's known as the throat of the weld. It's at a 45-degree angle, dead between the vertical side of the weld and the horizontal side of the weld. And the surface area that would fail would be right along that throat. You could kind of cross-hatch it down in there. If the thing was made of glass, I could even show it to you if it was made out of glass instead of steel. The area of a weld is equal to cosine of 45 degrees times the weld size times the length of the weld, and then, of course, if there's one on both sides, the length would be the one on this side and the one on that side. In this case, the area would equal to, let's just say that this weld has a size of 1 inch. Now, this picture is not a real good picture, because whoever drew it drew the weld size the same size as the plate. Most of this information will come up in later discussions, but in the real world, if you have a plate and it's welded to another plate, they will not let you weld all the way up to that corner. They want this weld height to stay down below that corner by about a 1/16 of an inch. And then 1/16? Oh, yeah. The reason is that's for inspection. If you let an unscrupulous welder get in there, he will heat the weld up so badly that he'll just burn the corner off rather than really build the weld up to the full 1 inch size. So if you make him stay away from that corner and don't burn it off, then the inspector can come by and see there should be about a 1/16 of an inch gap between the weld and the corner of the plate all the way around. It's real easy to inspect. So the weld that they have shown in this figure shouldn't really go all the way to the top. We'll assume it does, but it really should stand down from the plate about a 1/16 of an inch. So in our case, we'll take 0.707 times 1 inch, and that's what we have for the throat of the weld. That's the distance across the 45-degree plane on the weld. Then you multiply that times the length of the weld. That's about 7 inches long, and there are two welds, one on each side, and then that gives you the area of the weld resisting the forces. 9.9 square inches of weld. The interesting thing on a weld is if you were to also weld on the end of the plate, it also acts in shear, and therefore has the same area. Were that weld to fail, half of it would go with the plate, and half of it would stay on the base. And then that area, that added area, would merely equal to 0.707 times, it's a 1-inch weld, that gives me the throat dimension, times 6 inches, and I would simply add that to the 9.9 for the total area of the weld. The stress induced in a weld is a shearing stress. I don't care if you push on it, pull on it, twist it. You can do anything you want to a weld. The weld tends to fail in shear across a 45-degree plane. And you would simply take the load divided by the total area of the weld, and that'll give you the stress in the weld. All right. Now we go to twisting a bar. Oh, thanks, Kelly. Appreciate that. Oh, it's the focus. No wonder it's not going anywhere. Ah, yeah, there it is. Of course, no telling what it's focused like now. Try that. When you twist a bar, you also cause some stresses in the bar that are shearing stresses. When you twist the bar about its axis with a torque, this little fiber on the top of the bar resists that twisting, and a little fiber on the bottom of the bar resists that twisting, and they cause shearing stresses across the face of the bar. Now, the poor little guy in the middle of the bar doesn't really know what to do. As you notice, the guy on his top says we ought to go to the left. The guy on the bottom says we ought to go to the right. And so he says, phooey, I just won't do anything. And so there is no stress in the middle of the bar. The shearing stresses are actually distributed straight line, and they would be largest on the top, largest on the bottom, straight line. Here on the side they would be going the same direction, but basically they are a wiping stress across the face of the bar. Now, since there's not much stress in the middle of the bar, that's why a lot of times you'll see the bar is hollow. The fibers weren't doing very much work for you, and so the guy hated to waste that money in the middle fibers that weren't doing much work. For a small shaft, the shaft would probably be hollow. It's not hardly worth hollowing out the shaft to save the steel or to save the weight. If it's going in an aircraft, or if it's going to the moon, then they probably will take the center out because they're not so much worried about the recovery of steel they get. They're worried about having to haul that pound or 2 pound around with them for the rest of their life. Big old shafts, like a drive shaft in a car, will almost always be hollow because they don't want to waste that amount of steel. The stresses are of the wiping variety, and therefore they are shearing stresses, and so we give the symbol tau for the shearing stress involved is torque applied, outside radius of the shaft, divided by what's called J, the polar moment of inertia. J is simply a strength factor, It's given by pi over 2 times the outside radius to the 4th power minus the inside radius to the 4th power. And the equation's not good for anything except circular pipes and circular rods, and the circle, the hollowed out piece has to be in the middle of the bar or reasonably close. It's not good for square bars or structural steel square tubing. On page 12 is a short picture of the stresses. If I told you the radius of that bar was going to equal to 2 inches, and I told you that I was going to apply a torque to the bar, that torque was equal to 6 kip feet, then I ought to be able to tell you the stress in the bar. And you notice that the stress in the bar could care less what the bar is made out of. It's made out of wood, it's made out of plastic, it's made out of steel. The stress is the same. What matters on the bar about what it's made out of is whether it will withstand this magnitude of shearing stress. In our case, we'd be talking about 6 kip feet times 12 inches in a foot. Now there's our torque. Then we multiply that times the radius, 2 inches, and we divide it by the polar moment of inertia. Polar moment of inertia is pi over 2 times the outside radius raised to the 4th power. If we had a hole in it, we would subtract how much polar moment of inertia we had due to the inside piece that was missing. We don't have any inside missing piece, so we wouldn't bother even putting on that term. And it doesn't matter, but whatever that comes out, that is the shearing stress in the bar. Again, that shearing stress will be compared with allowables and determine whether or not the bar is acceptable. Okay, here on page 13 is, again, pretty symbolic of the type of question you're going to have to answer to just get the torques in the bar. And that's done using free bodies. The nice thing is there's nothing new. It works exactly like we worked for the bar in tension. If you want to know how much stress there is in bar CD, you simply cut through bar CD. You isolate it. You find out that there's 4 kip feet applied, and it doesn't seem to be any balancing kip feet running around loose. And so the torque in the shaft is 4 kip feet, and therefore the shearing stress is equal to 4 kip feet times 12 inches in a foot times the radius of the bar. The oldest trick in the book for a prof to give you the diameter when the controlling equation calls for the radius, 1 inch, divided by the polar moment of inertia, pi over 2, 1 inch raised to the 4th power. In a case like this, if the guy asked me for the maximum stress, I wouldn't have any idea where to look. I'd just probably look everywhere. If, on the other hand, there was more torque in this skinny piece of bar than any place else, I'd head for that place alone and not check anything else. Now then, to find the stress in bar BC, you'd say that the shearing stress in bar BC is equal to the torque. Well, in this case, isolating the entire structure, you'll notice I always go around the free end of the structure. I don't cut around the wall because I don't know what's inside the wall. I don't know how much torque is inside the wall. I could solve for it by statics, but that's a pain. And it may even get the wrong answer. It makes a lot more sense to cut around the free end of whatever we're working with. In this case, inside of this magic cloud, I see a 12 kip feet going one way and a 4 kip fighting it, and I can tell that the 12 is a winner. It's winning to the tune of 8. If this thing is to sit still, there can be no winners, and therefore the torque inside of section BC is 8 kip feet, which I multiply times 12 inches in a foot. That's my torque. Next I go for the C, TC over J. That's 1.5 inches. And divide by pi over 2 times, this bar is 1.5 inch radius raised to the 4th power. You'll notice as the bar gets a little bit bigger, it gets a lot stronger because the J, the strength, increases to the 4th power. So it doesn't take much extra steel on the outside of a shaft to give you a dramatic reduction in stress or increase in strength. And then the final thing, to check the stress in the last section AB, say the stress is equal to the torque. Alright, who's fighting who? Well, I got 2 guys pointing that way, that's 6. I got 1 guy going the other way, that's 12. So I'm out of balance by 6 kip feet. The out of balance is why I bought the shaft. 6 kip feet times 12, oops. And rather than move that, let's see. 6 kip feet times 12 inches in a foot times C, 2.5 over 2 divided by pi over 2 times 2.5 cut in half to the 4th power. And I got the shear stress in the shaft. Shear stress in the shaft is to be compared in the allowable somewhere, see if it's acceptable. I could also solve for the diameter were the guy to give me the torque and give me the allowed stress, then I could turn that around and solve for the diameter necessary. I'd simply pull out all of the D terms or all of the radius terms on the one side of the equation and stick all the other terms over on the right hand side. Alright, page 14. Quick and easy. I messed up the focus on this thing a minute ago. Let me get that straight again.
Put it back.
And then I'll stay away from that button. Much better. Alright. The torque in this section, 500. The torque in this section, 2,000. And you see what I'm doing. All I'm doing is isolating the right end of the shaft and adding up all the out of balance. The torque in this section, 0. Now that doesn't mean that we don't need a shaft there. It just means under the current loading condition that piece of the bar is not loaded. Obviously, probably they'll put a little more power to some other gear and take a little more out somewhere else, and then that number may not be 0, or the guy wouldn't have bought the shaft in that region. He'd have left it out. But right now it's not being used and it's not being twisted. Continuing, 5 and 15 is 2,000, take away 2,000, add 200, so I got 200 inch-pounds in that region. And finally, let's see, 15, 2,000, take away 2,000 is 0, 0, add 200, add 800, there's 1,000. What'd you say? You say 1,000?
Yep.
How'd you get that so fast? Cut off the other end, huh? And of course, that's right. As you cut off the other end, you ought to get the same answer no matter which end you cut off. So you might as well just cut off whichever end is most convenient and has the fewest numbers in it. You get the same answer either way you go. All right, now those kind of problems are usually pretty simple. The reason is the forces are easy to come by. As you see, we just saw for 5 or 6 forces inside of a bar without much trouble. Beams, on the other hand, usually have a continual change in the magnitude of how badly they're bent and how badly they are sheared. And in those cases, rather than being discrete changes in the magnitudes, there are continuous changes in the magnitude, and you need to be able to draw shear and bending moment diagrams in order to solve for the worst case. That shaft that we just drew a minute ago, you could probably design that shaft if it was all one size just by picking out the biggest torque and making sure the bar resisted that torque. On a beam, without being able to find that biggest value, the biggest moment, you can't design it. So the rules are, first thing you'll do is you'll use statics and solve for the reactions on the beam. Secondly, and we'll just go back to this slide, you'll find that any diagram you draw, if you can calculate how much area is underneath that diagram, it will predict for you, it will tell you how much the next diagram changes in its magnitude. So if I tell you that this diagram has an area of 6, then the next diagram is going to change the value by 6. Now the next rule is that the magnitude or the value or how high any diagram is, it'll tell you how much slope there is on the next diagram. So if I told you, look at this diagram, how high is it right here? And you say it's 8 high, then I tell you the next diagram right underneath that point has a slope of 8. And those properties are very handy. Finally, and we'll use this to make more sense, as we start to use it and then come back. If the load on the beam is a uniform load, same magnitude, just runs across the beam at the same height, then you'll be able to calculate a property on the next diagram called X-bar. And the value will be how high is the shear diagram, and then how fast is it being mashed down. It'll be the starting shear divided by the load rate. All right, those will make a lot more sense once we start doing them. As an example, on page 16, first thing we do is we solve for the reactions. You solve for the reactions by statics. You'd be best off to sum moments about some point, one of the reactions. You can sum moments about just about any point you like, but if you get rid of one of the reactions, then it's a lot easier to solve for the other one. So I'm going to sum moments about point A to solve for the reaction at C. First thing I'm going to do is I'm going to lie about the load. I'm going to go ahead and take this uniform load and concentrate it at a point. Okay, yeah. That load will be 300 newtons per meter tall. That's the height of a rectangle. The base is 6 meters across. That's the base of the rectangle. And therefore that's equal to 1,800 newtons, 1,800 apples. And what I'm going to do is I'm just going to put it at the centroid. Now what you have to really be careful is not to leave that lie on your load diagram. Because if you forget and draw the shear moment diagram for this untruth, it's going to look totally different from the real moment diagram. As soon as you find the reactions, it's legal to do that, but as soon as you find the reactions, then it'll be your job to take this load and spread it back out like it really is. Alright, so I'm going to put 1,800 newtons. I'm going to show it a little bit off just so I can see it. And I'm going to sum moments about A. The equation says sum moments about A is equal to 0 is equal to 1,800 times how far he is away from point A, 6 meters. I'm going to assume that is a negative tendency to roll, because if the 1,800 Newton force were to get away from me, he would roll not the way my hand is made, my right hand. He would actually roll down clockwise. Next, I see a 2,700 Newton meter. He has a tendency to roll plus. One of the most common mistakes is to multiply the 2,700 Newton meters times 9 meters. If you'll check your units, you'll see that can't be right. A moment is 1,800 newtons times 6 meters. That's a Newton meter, is the basic units of a moment. If you multiply the 2,700 Newton meters times 9 meters, you get a Newton meter meter. Nobody's ever found a use for a Newton meter meter. The 2,700 is already a rolling type of affair. It's already rotating. Then you solve, we've got to have the reaction in there. We'll say plus the reaction at C times his moment arm of 6 meters, and we can solve for the reaction at C. Reaction at C is 1,350 newtons. So we would stick that on the free body, 1,350 newtons. Then if you solve for some of the moments about point C and solve for the reaction at A, you'll find 450 for that reaction. Alright, that is the load diagram. The next diagram in the series is the shear diagram, and it is a summary of how badly the forces are acting across the axis of the beam. It's a very simple procedure to do these things. You just kind of follow the bouncing ball. You start on the left end of the beam at 0. You simply do what the loads tell you to do. In other words, you look back up one diagram and you say, what would you like to do? He says, I'd like to go up 450. You say, okay, I'll raise the value 450 higher than it used to be. Well, it used to be at 0, so now you are 450 newtons in the air. That's what we were saying a minute ago. The area, and that concentrated force is actually an area. It doesn't look much like one. It's just a very skinny, narrow area, but it's got an area of 450 newtons. And so as you go across that concentrated force, you simply jam the curve 450 newtons in the air. Now you continue to do what the diagram tells you to do. This diagram doesn't have anything in this region, and therefore that's what I'm going to do. I'm going to do nothing. I'm not going to go up higher. I'm not going to go up lower. Not until I see some new forces acting on the beam above will I move the magnitude. Now, how far you go as you move across is until something new happens. For instance, I was coming across the left end of the beam, out in the air, and all of a sudden I hit an upward pointing 450. The total distance I could go was about 1 atom, 1 micrometer, because that's how skinny the load was. And as I hit the other side of the load, I was supposed to be 450 in the air. Now the next jump, I can go all the way from A to point B, because nothing new happened in that region. How far I'll be able to go in the next jump is from B to C, because that's how far it is while something constant, something same old stuff is happening to me. I would go all the way to D, except for that reaction at C is in the middle, and I have to, as soon as I hit that, I have to do his specialized, what he wants me to do, namely he'll want me to jump up 1350 in the air. Now, how much this block, this rectangle, pushes the curve down between B and C is simply the area under the curve. So I got to be pretty good at calculating areas under curves. The area under that curve is a rectangle, so it's simply base times its height. Its base is 3 meters across. Its height is 300 newtons per meter. And therefore, that block is actually nothing but a bunch of sandbags. And there are 900 newtons worth of sand in those bags. Therefore, as I hit point C, those sandbags have been pushing down a total of 900. And therefore, I ought to be 900 lower than I used to be. Well, I was 450 above the line. If I intend to be 900 lower than that, then I'm going to be 450 newtons below the line at this time. Now, the next thing is how we get from point B to point C. How you get from point B to point C is pretty much based on the fact that if you would go 1 meter, you would enclose a third of this. If you go 2 meters, you have crossed 2/3 of it. If you go 3 meters, you've crossed 3/3 of it. And therefore, the intermediate points are 1/3 of the way down, 2/3 of the way down, 3/3 of the way down. You can also remember that we said that the value on any curve will predict the slope on the next curve. You'll notice that this value is constant, and that's why you see this slope is constant. Now, the mathematician, I'm going to turn this sheet over just to write something right quick. The mathematician would tell you that these curves stand one integral apart. The method we're actually doing is called a graphical integration technique. But he'd say, fully on that, he'd say a constant curve, he'd say that's like an x to the 0 curve. He'd say that curve turns into a straight, sloping line. And I'd ask him why, and he'd say, because an x to the 0 integrates into x to the 1. And what we just did proves he's probably right. The constant curve turned into a straight sloping line. I'd say, well, if it's that easy, tell me more. He'd say, well, that turns into a parabola. And I'd say, how come? He says, because you integrate x to the 1 power, you basically get x to the 2 power. Now, admittedly, you get a constant in front of that and some danglers off at the end, like a constant times x1 plus some x to the zeros. No telling what else is in there, but the basic shape of the curve is 1 power higher. He'd then say the next curve is a cubic, because x squared integrates into x cubed, and a quartic, which is an x to the 4th, and about that time I'd get bored and say, enough, enough. I see what you're doing. He would also tell me that I could find the value of any of these curves and turn it into the slope on the next curve, and that actually comes from calculus. So, that makes it pretty nice for me in this diagram, because all I got to do is find this point and this point, and I know how to connect the line up. I know to connect it with a parabola or a cubic or a straight sloping line. I choose a straight sloping line. Reason, the curve above it is constant in value, thereby turning this into one that is a first order curve. Below that point, you'll notice I've got a parabola showing. Alright, how about a break? What do you figure? 5 minutes okay? They'll tell us.
That'd be good.
Okay, 5 minutes fine, and we'll crank up the rest of this program.
Sounds good.